Welcome back. In this video, we uncover some sufficient conditions for Hamiltonicity. And of course, I'll start with a little bit of history, and then we'll take a look at some theorems. So first off, what's the idea here for sufficient conditions of Hamiltonicity? Well, the idea is to simply, observe that complete graphs, right? Complete graphs are all complete graphs of order. So I'll say Kn for n greater than or equal to 3 are Hamiltonian. Right, this should be obvious. There's a lot of edges in Kn. We can always find a Hamiltonian cycle, sort of without even really having to prove anything here. It's just obvious that we can find a cycle that contains every vertex. So these are all Hamiltonian. The idea is if a graph has a lot of edges, it's Hamiltonian. It should be Hamiltonian. There should be some property there that guarantees Hamiltonicity. But at the same time, we can also think of Kn as having high degree sums. So the degrees, the sum of any two degrees of the sum of any of the degrees of any two vertices is also very high in Kn, and so we might be led to believe that maybe there's some degree sum condition that guarantees Hamiltonicity. On the other hand, the minimum degree of Kn is also very high, and so maybe there's a minimum degree sum condition or a minimum degree condition that guarantees Hamiltonicity. So here we're thinking about is there a degree sum condition, minimum degree condition, minimum degree condition to guarantee Hamiltonicity. In fact, there are, and we'll see both of those. These are the results of Ore and Paul Dirac. So a little bit of history, Gabriel Dirac. Paul Dirac, you might have heard of before, is a Nobel Prize winning physicist who is famous for an equation that describes half-spin particles. I'm not a particle physicist, but it describes half-spin particles. So this would be like electrons and quarks that exhibit some sort of symmetry. So Paul Dirac was able to come up with this equation that was able to describe these particles. Eventually, this would be he would do work with Schrödinger and develop the Schrödinger wave equation, and together they won a Nobel Prize for their work in particle physics and really quantum mechanics. You can see this as sort of a joining of special relativity to quantum mechanics, which is a big deal because, as you may or may not know, general relativity has never really been extended to quantum mechanics, and that's sort of the huge result that people would like to get now, is to develop a theory of gravitation that is consistent with quantum mechanics. But special relativity was done. This was by the work of Dirac and Schrödinger, and again, if you're more experienced with physics than me, maybe I've said something not 100% correct there, but that's the general idea, unifying special relativity and quantum mechanics, and that was Dirac and Schrödinger did this. Now, Dirac had a stepson, Gabriel Dirac, who did work in mathematics, was very interested in mathematics from a very young age, and did some work in graph theory, and actually we can kind of say that Dirac was one of the first people to really get graph theory going and bring a lot of attention to graph theory, and this was in the 1950s. He was doing this work. So the result we'll look at from Gabriel Dirac was a sufficient condition for Hamiltonicity, and again, that was in 1952. By the way, in Hungary at the time, this is principally the place where graph theory was happening, was in Hungary. And that's where Dirac was doing this work. Now, Ore, on the other hand, I don't have a lot of historical context for Ore, but Ore also gave a more general condition for Hamiltonicity in 1960. So how I've laid out this mini lecture here is we're going to first, and how the book is laid out, indeed, is we'll first give Ore's result, and then use that to see Dirac's result as a corollary of that one. Of course, this is reverse chronological order, but it makes proving Dirac's result a lot easier. So we won't actually see Dirac's original proof. We'll see Ore's proof and use that to prove Dirac. All right, so let's see. I want to remind you for a second of these degree sum results that we've seen. So remember that we've encountered this before in Theorem 2.3 to guarantee that a graph is connected. Remember, if the degree sum, the non-adjacent degree sum, so if degree of u plus degree of v is at least n minus 1 for non-adjacent vertices, for all non-adjacent vertices of the graph, that guarantees the graph is connected. As we'll see, it actually turns out we get a lot more bang for our buck here. We get more than just that the graph is connected. We'll see that later on, but this is an example of these non-adjacent degree sum results that I'm talking about. You also worked a problem in 3.1. So dealing with non-separable graphs, that if the degree of u plus degree of v is at least n for non-adjacent vertices, then g is non-separable. So this idea of non-adjacent degree sum is so prevalent in graph theory that finally we're going to come up with some notation for this. We call this sigma 2 of g. We use this to denote the minimum of the degree sums of any two non-adjacent vertices in a graph. So sigma 2 of g is the minimum of this set of non-adjacent degree sums. And so these could be rephrased in terms of sigma 2. We could say that if a graph g, if sigma 2 of g is at least one less than the order, then it's connected. If sigma 2 of g is at least the order of the graph, then it's non-separable. And there are lots of results of this type. In particular, we have this for Hamiltonicity. And this is Oystine-Ore's result. Let G be a graph of order n at least 3. If sigma 2 of G, so minimum of the non-adjacent degree sums, it's at least the order of the graph, then G is Hamiltonian. So notice this is the same sufficient condition to guarantee that a graph is non-separable, but we actually get a lot more bang for our buck. We actually get that G is Hamiltonian if sigma 2 of G is at least n. So let's take a look at a proof of this. Let's prove this one. Prove Ore as a result. Okay, so how does this work? Well, we're going to suppose that it's false, so assume to the contrary. Suppose this is false. Then what does that mean? Then there is a graph, let's say G, of order at least n at least 3, such that sigma 2 of G is at least n, but G is not Hamiltonian, so it doesn't contain a Hamiltonian cycle. All right, so as we've done in the past for these proofs by contradiction like this, we're going to choose a maximal example in a certain sense. So what we want to do here is we want to add edges between non-adjacent vertices. Add edges between non-adjacent vertices. I need to look at the wording. We want to add as many edges as possible between non-adjacent vertices so that the resulting graph is not Hamiltonian. Right. I actually want to change. I want to change the symbols I'm using here. So graph G. I'm actually going to call this initial graph H. So H is our graph that is that is not Hamiltonian, but meets this degree sum condition. We add edges, all possible edges between non-adjacent vertices of H, so that the resulting graph, and we're going to call this one G, is not Hamiltonian. So that is G is a maximal non-Hamiltonian graph. In the sense that, so i.e. that is G plus UV, So if we add any edge to G for non-adjacent vertices, so if we add any edge to G, then G is Hamiltonian. So it's maximal in that sense. All right, so one thing to note here is that G is not complete. So G is not complete, for otherwise it would be Hamiltonian. So what does this mean? That means there exists xy that is not an edge of the graph. So there exists, let me be more specific. There exists vertices x and y in the graph that are non-adjacent, and such that if, that are non-adjacent. That's all I want to say. There's two vertices that are non-adjacent. And in particular, G is maximal non-Hamiltonian. So if we add edge xy to the graph, then it will be Hamiltonian. So G plus xy is Hamiltonian. So there is a Hamiltonian cycle. I wanted to do a fancy H. Sometimes, and this is how my graph theory professor did it, sometimes we use this fancy H to stand for Hamiltonian so that it takes less time to write it all out. It's a big word. So there's a Hamiltonian cycle. Let's call it C. Now, necessarily, this Hamiltonian cycle C has to contain this edge xy, right? Otherwise, there would have been a Hamiltonian cycle in G, but we know G was maximal non-Hamiltonian. So we can say, let me just make a note here, C must have xy consecutive. So it must contain these two vertices consecutively. That is, xy is an edge that's used. Again, otherwise G would have been Hamiltonian, which we know it's not. So that means we have this Hamiltonian cycle, x and y. So how about I lay it out like this? So we have x here. I'm going to call it V1, V2, V3. I'm going to call this one V sub I minus 1, V sub I. Finally, to, let's say, V sub n minus 1 and V sub n, and this will be my vertex y. So here, our Hamiltonian cycle in G plus xy would look like this. And so we actually get a Hamiltonian path in G, right? If we remove this edge xy, we get a Hamiltonian path in G. So I can say, let's say P is a Hamiltonian path in G. Right, so G plus xy has a Hamiltonian cycle. X and y must be adjacent in it. So we have that picture there. If I remove the edge xy, I get this path P, which is a Hamiltonian path in G. Okay, so now suppose, and necessarily x and y are not adjacent in G, remember. So suppose x vi is an edge for some I. So let's say x is adjacent to another vertex on this cycle. So x vi is an edge. Well then, let me draw this in dotted. If y vi minus 1 is an edge, then I would have a cycle. I would have a Hamiltonian cycle going from x, so that's v1 to vi, going over here to y, coming back to vi minus 1, and then proceeding back to v1. And so what that means is that If XVI is an edge, then YVI minus 1 is not an edge. So what this means is that for every vertex adjacent to X, Y is not adjacent to some vertex. And this is where we're going to get our contradiction. So every vertex that X is adjacent to, there's some other vertex that one's adjacent to that Y is not adjacent to. And so it follows that the degree of Y is at most, so we know it's not adjacent to X, so n minus 1, minus the degree of X. And so what we get, this tells us that the degree of X plus the degree of Y is at most n minus 1. And then since X and Y are not adjacent, this is a contradiction. That means there must have been. So why is this a contradiction? So remember we added a bunch of edges. We started off with this graph H. We added a bunch of edges to it, but we only added edges between non-adjacent vertices. And so if we take this back, it means X and Y must have been, the degree of X plus degree of Y must have been at most n minus 1 in H. And so it follows that that's a contradiction, because our assumption was that the degree of X plus degree of Y was at least n for all non-adjacent vertices X and Y. And that proves it. So that's Oistein-Ore's result, and as we'll see in the next video, this idea of adding edges between non-adjacent vertices is going to come up again. This technique is going to be applied again. So that's Ore's result. If the degree sum is at least n for non-adjacent vertices, then G is Hamiltonian. So that's pretty cool. Here we get Dirac's theorem now, which says that if G is a graph of order n at least 3, such that its minimum degree is at least half of the vertices, then G is Hamiltonian. So why does this follow from Ore's result? Well, if G is complete here, so let's suppose we have the hypothesis satisfied. If G is complete, then we're done, it's Hamiltonian. If it's not complete, then there's at least 2 vertices that are not adjacent. By this minimum degree condition, the sum of those 2 non-adjacent vertices, or any 2 non-adjacent vertices, will be at least n because of this degree sum condition, right? And that will guarantee then by Ore's result that G is Hamiltonian. And so that's Dirac's result, seen as a corollary of Ore's result. So finally, we'll look at one more theorem here concerned with degree sum, and that is that if G is a graph of order at least 2, if the minimum degree sum is at least n minus 1, then G has a Hamiltonian path. So remember, this is the same condition that guaranteed a graph was connected in terms of degree sum, and we actually get a lot more bang for our buck here. We can see that G actually has a Hamiltonian path. So why is this true? Well, we're going to use this technique that we used in Eulerian graphs. We're going to modify our graph a little bit and use a Hamiltonian cycle that we find there and use this to produce a Hamiltonian path. Okay, so let G be a graph of order at least 2, such that the minimum non-adjacent degree sum is at least n minus 1. And I'm going to form a new graph. I'm going to let H be the join of K1 and G. So remember, the join operation takes K1 and makes it adjacent to every vertex of G. So here I have G, some graph that meets this degree sum condition, and now I take K1 and I join it to every vertex of G. And that gives me a new graph, H. I'm going to call this vertex W, this new vertex that I added to form H. So what can we say now? Well, we can say that, so look, W is adjacent to everything, so we don't have to worry about that with degree sum. But any two vertices that were not adjacent in G, remember their degree sum was at least n minus 1, but now that we've added W in, the minimum degree sum of those two vertices would be at least n. We've added one edge to W, one edge here to W, so we've added 2 to the minimum degree sum. So we can say it follows that sigma 2 of H is at least n plus 1. And that's important. We need it to be at least n plus 1 because H has order n plus 1. Since H has order n plus 1, it follows from Theorem 6.1 that G has a Hamiltonian cycle. Let's call it C. So, sorry, the H has a Hamiltonian cycle. We can't guarantee G has one. But certainly H has one because it meets this degree sum condition. Sum of any two non-adjacent vertices is at least the order of the graph. And so we have a Hamiltonian cycle. Well, again, well, I guess, yeah, W has to occur somewhere in that Hamiltonian cycle. So we have the cycle going on in here, and at some point we hit, right, W has to be involved in the cycle. We hit W, and then it comes back out and goes back to a vertex of G. So we can say necessarily there are vertices U and V in the vertex set of G, such that U, W, V occurs consecutively in C. Then C minus W, so get rid of this, this vertex W, remove this, is a Hamiltonian path in G. In G now. So that's the idea, is find this Hamiltonian cycle, remove these edges and this vertex, and then we're left with a Hamiltonian path in G. And that does it. So here we have now a minimum degree sum condition for being Hamiltonian, that's Dirac's result, and this degree sum condition to guarantee Hamiltonian, that's Ore's result, and we also get another corollary of that degree sum condition, a little bit less, to guarantee a Hamiltonian path. And so that's pretty good. In the next video, we're going to explore this idea, this method we used in Ore's result, this idea of adding edges to a graph to see another sufficient condition. This is going to be called the closure of a graph. I'll see you in the next video.